This is a report about the faults beneath the west coast of the United States and why they have been on the minds of scientists this year. On June 19th, 2026, a group of researchers shared a finding that drew wide notice. They reported that part of the San Andreas Fault in Southern California, along with a neighbouring fault called the San Jacinto, is carrying more strain than it has in roughly 1,000 years. The rock there has been locking in place for more than a century, and the stored pressure has reached a high mark. If a calm look at this steadies you more than a loud one, you might subscribe, so the next report reaches you. That June finding did not stand alone. In the same stretch of months, separate studies pointed the same way. One mapped a hidden tangle of moving rock under Northern California. Another found that two of the coast's largest faults may be more connected than anyone had thought. This report walks through what these faults are, what the new measurements really show, what scientists know, and what stays an open question. This past June, a team of researchers reported that a stretch of the San Andreas Fault in Southern California is wound tighter than it has been in about 1,000 years. The same went for a second fault that runs close beside it, called the San Jacinto. Both lie less than 60 miles northeast of downtown Los Angeles. That is close enough to reach by car in about an hour. The word the scientists used was locked. Along most of a fault, two huge blocks of rock are trying to slide past each other. Friction holds them in place. They do not move smoothly. Instead, the strain builds in the rock around the stuck spot year after year until something finally gives. The new work measured how much of that strain has piled up on these two faults, and the answer was a lot. More, by their reckoning, than at any point in the last 10 centuries. The lead author, a geophysicist named Liliane Burkhardt, was careful about how she framed it. The point was not to frighten anyone. The point was that the system is sitting at a high mark, and that planning for it now makes more sense than reacting to it later. A geologist who reviewed the work put it simply: people talk loosely about a fault being overdue. It is another thing to have a careful physics-based estimate that the strain is at a 1,000-year peak. Here is why two faults so near each other matter together rather than apart. The San Andreas and the San Jacinto both trace the same deep boundary, the seam where two pieces of the Earth's outer shell meet. The Pacific side and the North American side have been grinding past each other for a very long time. When rock is squeezed and held for a century without release, it behaves like a spring you keep winding. The energy does not disappear. It waits. The finding that drew the most attention was not just the high strain, it was where the strain sits. The two faults nearly touch at a mountain corridor north of the city, a place that can act like a gate between them. If a quake starts on one fault and reaches that gate while the rock is this tightly wound, it may not stop. It may carry across onto the neighbour. A break that jumped from one fault to the other would shake a far wider area than a break on either fault alone. None of this is a forecast of a date. No one can say when. The researchers were clear that their work does not predict timing, and that no method can. What it does is change the odds in a way worth taking seriously. The ground there has been loading for more than 100 years, and the gauge now reads higher than it has in a millennium. It helps to hold the scale in mind without letting it tip into alarm. Southern California has always lived on a moving boundary. The mountains, the valleys, the very shape of the coast were built by this motion over millions of years. Small earthquakes happen there constantly, most of them too faint to feel. The new measurement does not mean the ground is about to open. It means one specific corner of a familiar system has reached an unusually high level of stored strain, and that this corner happens to sit near a great many people. That last part is what gives the finding its weight. The faults pass close to San Bernardino, Riverside, and the long desert stretch of the Coachella Valley, as well as the northern edge of the Los Angeles region. Major roads, rail lines, water canals, and power routes thread through the same ground. A large quake there would not be a single point of damage. It would touch many systems that millions of people rely on at once. So this is where the report begins. One fault, and the fault beside it, measured at a 1,000-year high in strain, near one of the most crowded parts of the country. It is a real finding from real instruments, and it is the kind of thing that rewards a calm, close look rather than a quick scare. To understand why a number like that should matter, and why scientists say these faults are stirring, it helps to step back to something simpler first. Before the gates and the strain gauges, There is the plain question of what a fault actually is and what it means for one to come back to life. A fault is a crack in the Earth's outer shell where two slabs of rock move in different directions. That is the whole of it, at the start. The rock is not soft or molten near the surface. It is hard and brittle, and when two blocks of it try to slide past each other, they catch. Most faults spend most of their lives stuck. That sticking is the key to everything that follows. The deep forces driving the rock never pause. They keep pushing steadily, while the fault itself refuses to budge. So the strain has to go somewhere, and it goes into the rock on either side of the locked patch. The ground bends and stores the energy, the way a wooden ruler bends when you press its ends toward each other. You can press for a long time and see almost nothing. Then the ruler snaps, all at once. An earthquake is that snap. The locked rock finally loses its grip. The two sides lurch into the position they had been resisting, and the stored energy races out as shaking. The bigger the patch that breaks, and the more strain it was holding, the larger the quake. A small fault that slips a little gives a small tremor. A long fault that breaks along many miles can shake a whole region. This is why the phrase coming back to life can mislead, if you take it the wrong way. The rock is not asleep and then awake. The deep motion never stopped. What changes is whether a fault is quietly building toward a slip, or quietly releasing strain in ways too small to notice, or sitting in between. When people say a fault has come back to life, they usually mean one of two things. Either the strain has climbed to a level that makes a slip more likely soon, or new instruments have finally let us see motion that was there all along. Both of those are happening on the West Coast right now, and it is worth keeping them separate. The Southern California finding is the first kind. The strain on those faults has genuinely reached a high mark. The second kind is just as important and far less frightening. Better sensors and sharper methods are revealing faint activity that older tools simply missed. A fault can look newly active on a map only because we have started watching it more closely. There is one more piece that surprises people. Not every fault stays locked. Some sections creep, sliding along slowly and steadily, a little each year, without ever building to a sudden break. A creeping section can act like a relief valve, letting strain bleed off gently. A locked section does the opposite. It holds everything in until the moment it lets go. The same fault can creep in one stretch and stay firmly locked in another, and the locked stretches are the ones that store the energy for a large quake. Knowing that distinction changes how you read the news. When scientists report that a section is locked, they are telling you it has not been releasing strain the easy way. The energy has been collecting. When they report that strain has reached a 1,000-year high on a locked section, they are saying the bend in the rock is deeper than it has been in a very long time. Neither statement names a day. Both describe a condition. It also explains why measuring strain is hard and why the recent work mattered. You cannot see the bend in the rock with your eyes. The land looks still. The strain shows up only in careful tracking of how the ground shifts over years, in how older quakes are spaced through time, and in models that turn those clues into a number. Reaching a clear figure for stored strain is a real achievement, and reaching one that points to a 1,000-year peak is the sort of result that makes other scientists look twice. So a fault coming back to life is really a story about pressure and attention. The pressure is the strain stored in bent rock. The attention is our growing ability to watch faults that once kept their secrets. To see why the West Coast holds so much of both, the next step is to look at the boundary itself, the slow collision that put all these faults here in the first place. The whole story sits on a simple fact of geography. The outer shell of the Earth is broken into a few enormous slabs called plates, and they drift slowly, carrying the continents and oceans with them. The west coast of North America is where two of the largest meet. The Pacific Plate, which holds most of the ocean floor, presses against the North American Plate, which carries the continent. The line where they meet runs the length of the coast. These two are not crashing head-on, and one is not diving cleanly under the other, along most of California. They are sliding past each other side by side in opposite directions. The Pacific side is creeping to the northwest. The continent holds to the southeast. A boundary where two plates grind past each other, like this is the kind that builds the San Andreas and its many cousins. The speed sounds almost gentle. The two plates move past each other a couple of inches in a year, about the rate your fingernails grow. You would never feel it, but the motion never quits, and small numbers add up over long time. In a single human lifetime, the two sides shift by several feet. Over a few thousand years, by the length of a city block. The rock has to absorb every bit of that, and where it cannot slide freely, it stores the difference as strain. That stored difference is the fuel for earthquakes, and it is why a sliding boundary is so productive. The plates want to move a couple of inches a year. The locked faults refuse to let them. So the gap between what the plates want and what the faults allow keeps growing, held in the bent rock, until a fault breaks and catches up to the motion in a few violent seconds. A large quake on the San Andreas can move the two sides past each other by many feet in an instant, paying off decades of debt at once. Here is the part that reshapes the picture. The boundary is not one clean line. It is a wide, frayed band of many faults running roughly parallel, sharing the work of moving the plates. The San Andreas carries the largest share, but it does not carry all of it. The San Jacinto takes some. Other faults take more. The motion is spread across a zone tens of miles wide, which means a great deal of ground in California is quietly taking part in the same slow grind. That spreading explains why two faults can reach high strain together, as the southern faults have. They are not separate machines, they are partners dividing one job. When the load on the boundary builds, it builds across the whole band, and faults that sit near each other feel the same deep push. It also explains the gates, the spots where one fault nearly meets another, and a break on one can spill onto the next. The boundary changes character as it runs north, and that matters for the rest of the report. Through most of California, the plates slide past each other and the San Andreas rules. But off the far northern coast, the simple side-by-side motion ends. There the ocean floor begins to dive beneath the continent, a different and more dangerous kind of boundary, and a third plate enters the scene. That northern corner is where some of the year's strangest findings came from. For now, the thing to hold on to is the engine. Two great plates, sliding past each other a couple of inches a year, never resting, putting strain into a wide band of faults along the entire coast. Every fault in this report draws its energy from that one slow motion. The differences between them come down to how each one handles the load, whether it creeps or locks, and how it sits next to its neighbours. The fault that carries the most of that load, and the one whose name most people already know, is the San Andreas itself. To understand why a measurement on its southern end made news around the world, the next step is to walk its length and see where it runs tight and where it runs loose. The San Andreas Fault runs for about 800 miles, almost the entire length of California. It comes ashore near the far northern coast, cuts down past the San Francisco Bay region, runs along the dry edges of the Central Valley, and bends through the mountains east of Los Angeles before fading into the desert near the Mexican border. If you have driven California, you have crossed it, probably without knowing. It is the main seam of the whole boundary, the single fault that carries the largest share of the plate motion. That status is what makes it the one people name. It produced the great San Francisco earthquake more than a century ago, the one that, with the fire that followed, destroyed much of the city. It is the fault that sits behind the phrase "the big one" in most people's minds. But the San Andreas does not behave the same way all along its length, and that is the detail that matters most here. In its central stretch, through the lonely country near the town of Parkfield, the fault creeps. The two sides slide past each other slowly and almost steadily, easing the strain off a little at a time. That creeping section rarely stores enough energy for a giant quake. It pays its debts in small change. The ends behave differently. To the north and especially to the south, the fault locks. It grips and holds, building strain for a long time, and then releases it in a large earthquake rather than a slow slide. The southern stretch, the part that bends through the mountains near Los Angeles and runs out toward the desert, is firmly in this locked group. And the southern stretch has a second uncomfortable feature. It has gone a long time without a great quake. That long quiet is not reassuring. On a locked fault, quiet means the strain has been collecting without release. The southern San Andreas has not produced a major rupture in more than 3 centuries, while the plates kept sliding the whole time. Every year of calm, there is another year of strain banked in the rock. That is the backdrop against which the June finding lands. When researchers say the strain is at a 1,000-year high, they are describing a section that was already known to be loaded and overdue, and they are putting a sharper number on just how loaded it has become. There is a common picture of the San Andreas as a single gash you could stand beside and watch. The reality is messier and more important. Near its southern end, the fault frays into several strands, and the San Jacinto, the partner fault from the earlier finding, runs alongside it through this region. The two are close enough that geologists study them as a connected system rather than as strangers. They share the load, and they may share a rupture. This is also where the densest population sits. The southern San Andreas does not run through empty land. It threads past fast-growing cities, beneath highways and water lines that supply tens of millions of people, and through the mountain passes that connect the coast to the interior. A fault can be dangerous because it is powerful, or dangerous because of who lives near it. The southern San Andreas is both. Put those facts together and the worldwide attention makes sense. This is the principal fault of the boundary. Its southern section locks rather than creeps. It has been quiet in the worrying way for a very long time, and new work says the strain there has reached a level not seen in 1,000 years, right where it presses close to its sister fault and close to millions of homes. The single feature that ties the two faults into one worry is the place where they nearly meet, a mountain corridor that can pass a rupture from one to the other. Scientists have a name for that kind of spot, and understanding it is the next step. Northeast of Los Angeles, the mountains part to make a broad, low corridor called the Cajon Pass. Travelers know it as the place where a major interstate climbs from the coastal plain toward the high desert. Trains use it. So do the pipelines, power lines, and aqueducts that carry fuel, electricity, and water into and out of the Los Angeles region. It is one of the busiest seams of infrastructure in the American West. It is also where the San Andreas and the San Jacinto faults come close together, and in the recent study the pass plays a special role. The researchers describe it as a kind of gate, a junction that can decide how far a rupture travels. When an earthquake breaks along a fault, the tear races outward from where it started. Usually it runs until it reaches a spot where the rock changes, or the fault bends too sharply, or a gap interrupts it. Such a spot can stop the rupture, or if the conditions are right, the rupture can jump the gap and keep going onto a neighbouring fault. The Cajon Pass is one of those decisive spots. A break that begins on the San Andreas and arrives at the pass might halt there, leaving a serious but contained quake, or it might pass through the gate and spread onto the San Jacinto, turning one fault's rupture into a shared one. The same is true in reverse. The gate works in both directions. What sets the gate's mood is the strain stored in the rock around it. This is where the year's finding becomes more than a number. The team reconstructed how a strain is built across this junction and concluded it sits at that 1,000-year high. A gate that is loosely loaded tends to stop a rupture. A gate wound this tight is more likely to let one through. The researchers' deeper point was about that balance. The amount of strain across the junction may decide whether the next earthquake stays small and local or grows into a much larger shared break. It helps to picture the difference in plain terms. Imagine a fire that reaches a fire break. If the brush beyond is damp, the fire stops at the line. If the brush is bone dry, the fire leaps the break and runs into new ground. The Cajon Pass is the fire break. The stored strain is how dry the brush is. The June finding says the brush right now is very dry. The reason this matters so much comes back to everything threaded through the pass. A rupture that stays on one fault would be severe. A rupture that crosses the gate and runs onto both faults would shake a far broader region, and it would do so across the exact corridor that carries the basics of life into Southern California. Highways, rail, fuel, power, and water all funnel through the same narrow ground. Damage there would not be one problem. It would be several at once, in the worst possible place for keeping a region supplied. None of this means the gate is about to open. A loaded junction is a condition, not a countdown. The researchers were direct that they cannot say when, and that the value of the work is in planning, not prediction. Emergency managers can treat a joint rupture across the pass as a realistic case to prepare for, rather than a far-fetched worst case to wave away. That shift, from unlikely to plausible, is the practical heart of the study. It is also a good example of how earthquake science actually advances. It rarely arrives at a date. It arrives at better odds and clearer mechanisms, knowing that the pass can act as a gate, and that the gate is tightly loaded, tells you where to look and what to prepare for, even when it cannot tell you the hour. That raises the obvious question of trust. How can anyone claim to know the strain across a junction is higher than it has been in 10 centuries, when no one was measuring it 10 centuries ago? The answer lies in how scientists read the long memory of the rock, and that is the next piece of the story. The claim that gives the study its force is the one that sounds impossible at first. The strain across these faults, the researchers said, is higher than at any time in roughly 1,000 years. No instrument existed 1,000 years ago. No one stood in the Cajon Pass taking measurements while the rock slowly bent. So the honest question is how anyone could know. The answer is that the rock and the landscape keep records, if you learn to read them. Faults leave a history in the ground around them. Each large earthquake of the past shifted streams, offset old soil layers, and left scars that a careful geologist can date. By digging trenches across a fault and reading the disturbed layers, researchers can work out roughly when past great quakes struck and how much the ground moved each time. Stack enough of those events together and a rhythm appears, a record of how often the fault has let go and how much strain each release carried off. The recent team used that kind of long history as the foundation, then went a step further. They built a model of the two faults and the junction between them, and they ran the clock forward across the last 1,000 years. Starting from the known past quakes, the model adds up the strain the plates deliver year by year and subtracts the strain released in each earthquake. What remains is an estimate of how much strain is stored at any given moment. Carried up to the present, that running balance is what reached its peak. The strength of this approach is that it rests on physics rather than on a hunch. People have long said the southern San Andreas feels overdue based on how long it has been quiet. That is a fair instinct, but it is only an instinct. A model that tracks strain in and strain out, anchored to dated past quakes, turns the instinct into a number with reasoning behind it. One outside scientist made exactly this point. The familiar idea that pressure builds over time is old news. The new and useful part is a grounded estimate that the system is sitting at a 1,000-year high and a sense of what that does to the gate between the faults. It is worth being plain about the uncertainty too, because honest science includes it. A reconstruction like this is not a photograph. The dates of ancient quakes carry error bars. The model makes assumptions about how the faults share the load. The 1,000-year figure is a careful estimate, not a stopwatch reading. The researchers know this, and it does not weaken their main message. Even with the uncertainty, the work points clearly in one direction. The strain is high, higher than the long record suggests is normal, and concentrated at the worst junction. There is a fresh wrinkle that makes the method stronger than older versions. Earlier studies often treated each fault on its own, asking when this fault or that fault might break. The new work treats the two faults and their shared gate as a single system and tracks how strain moves across the boundary between them. That is harder to model, but it is closer to how the rock behaves. Faults that sit this close do not wait politely for their turn. They influence each other, and a model that captures the link can say something the single fault studies could not. It can speak to whether a break is likely to stay contained or to spread. This is the quiet engine behind the headline. The dramatic phrase is the 1,000-year high. The real work is the patient reading of trenches, the dating of old quakes, and the careful bookkeeping of strain in and strain out, fault by fault and year by year. It is slow, unglamorous science, and it is exactly the kind that earns trust because every step can be checked. Once you accept the number, the natural next thought is what it would actually mean on the ground. If the gate did open, and the rupture did spread across both faults, how large would the quake be, and who would feel it? That is the scenario the researchers laid out, and it is the next part of the story. The researchers put a size on the worst case, and they did it carefully. A rupture that crossed the Cajon Pass and ran along both the San Andreas and the San Jacinto could reach a magnitude of about 7.4 to 7.8. That range matters more than it might seem, because of how the magnitude scale works. Magnitude is not a simple ruler, where 7 is just a bit more than 6. Each whole step up the scale means the ground releases far more energy, roughly 30 times as much per step. So a magnitude 7.8 is not a little stronger than a 7. It is in a different class entirely, the class of earthquakes that reshape cities. The difference between a single fault break and a joint rupture across the gate is the difference between a severe quake and one of the largest that this part of California can produce. The reason the joint rupture is worse is not only the higher number, it is the reach. A bigger break means a longer tear in the ground and a wider circle of strong shaking. A quake confined to one fault would hit hard in a defined area. A quake that runs across both faults would send severe shaking across a much larger region at the same moment, leaving less unshaken ground nearby to send in help. The places in that reach are home to a great many people. The faults pass close to San Bernardino and Riverside, two large inland cities, and run out along the Coachella Valley, the desert corridor that holds Palm Springs and the farms and towns beyond it. The northern edge of the sprawling Los Angeles region sits within range as well. A joint rupture would not strike one town. It would shake a broad inland swathe of Southern California in a single event. Then there is the matter of what runs through that ground, which the earlier chapter touched and which becomes vivid here. The same passes and valleys that carry the faults also carry the region's lifelines. The aqueducts that bring water from far away cross these faults. So do the main highways, the rail lines, the fuel pipelines, and the electrical corridors. A large joint rupture could damage many of them in the same minute. The first hours after such a quake would be defined not only by collapsed structures but by water that stops flowing and power that goes dark across a wide area. It is important to hold this scenario at the right temperature. It is a credible worst case, not a prediction of what will happen next. The fault could also break in a smaller, contained event. It could stay quiet for years yet. The researchers did not say a joint rupture is coming. They said the conditions now make it a realistic possibility worth planning for rather than a remote nightmare to dismiss. That is the practical shift, and it is a calm one. The work moves a joint rupture from the far edge of the imagination to the list of things responders should plan around. What that planning looks like is reassuringly ordinary and worth stating because it steadies the picture. Emergency managers can map which water and power lines cross the faults and harden or reroute the most critical ones. Cities can strengthen the buildings most likely to fail. Households can keep enough water and supplies to last several days without outside help, since a joint rupture might cut a region off for exactly that long. None of this requires panic. It requires the kind of preparation that a 1,000-year strain reading makes sensible rather than paranoid. There is also a longer lesson in the scenario. For decades, hazard planning often treated faults one at a time, asking how big a single fault could go. The new work argues that the dangerous question is sometimes how faults combine. A gate that lets a rupture spread can turn two moderate threats into one large one. Preparing for the combination, not just the parts, is the takeaway the researchers most wanted to land. That idea, that faults act together rather than alone, turns out to be the thread running through the whole year's findings. It showed up most strikingly far to the north, off the coast of Northern California, in a discovery built not from giant quakes, but from the smallest tremors scientists can detect. That is where the story goes next. Far to the north, off the coast of Humboldt County, a different group of scientists spent the past year listening to earthquakes almost no one will ever feel. These were tremors thousands of times weaker than the smallest shaking a person notices. On their own, each one is nothing, a faint stir deep in the crust. Gathered by the thousand and read together, they turned into a map of hidden ground. The work was published in a major science journal in the winter, and its setting is one of the most complicated corners of the entire coast. This is the region where the San Andreas system, sliding along through most of California, runs into the very different boundary to the north, where the ocean floor dives beneath the continent. Where those two systems meet, the rock is broken and tangled in ways that have never been fully understood. It is also a region capable of producing powerful and destructive earthquakes, which is why the effort to understand it matters. The motivation behind the study was stated plainly by one of its authors. If you do not understand the basic tectonic processes in a place, it is hard to judge its earthquake hazard. You cannot rate a danger you cannot map. For this stretch of coast, the map had always been rough. The textbook picture showed a few large plates meeting at a point, but real earthquakes there kept behaving in ways the simple picture could not explain. The tool the team reached for is one of the more elegant ideas in modern earthquake science. Deep in the crust, far below where ordinary quakes happen, the rock is hotter and behaves less like something brittle, and more like something that can ooze under pressure. Where plates slide past or over each other at those depths, They produce a special kind of tremor, very small and low in pitch, called a low-frequency earthquake. These tiny events cluster in swarms, and they happen exactly along the boundaries where deep rock is on the move. Find them, and you have found the hidden seams. What makes them so useful is that they go where no instrument can. No one can drill miles down to watch plates grind together, but the faint earthquakes are made right at those grinding surfaces, and they travel up to the seismometers at the surface. By collecting enough of them and pinpointing where each one came from, the researchers could trace the shape of boundaries buried far below, the way you might map a dark room by listening to where the echoes come from. The lead author offered a comparison that captures the whole problem. Studying this region, he said, is like studying an iceberg. You can see a small part at the surface. The real work is figuring out the shape of the far larger mass underneath. For a long time, scientists had only the visible tip of this seismic zone, the faults and quakes near the surface. The tiny tremors gave them, for the first time, a way to feel out the hidden bulk below. There was a long-standing clue that the hidden part held surprises. Years ago, a strong earthquake of magnitude 7.2 struck this region at a depth far shallower than the simple plate picture said it should. That mismatch nagged at researchers. It suggested the arrangement of rock down there was not what the map showed, that something in the structure was off. The mismatch sat unexplained for years, a loose thread waiting for a tool sharp enough to pull it. The swarms of faint tremors became that tool. They did not just confirm the rough picture. They revealed that the region is far more intricate than anyone had drawn, with moving pieces that had gone entirely unmapped. That is the discovery at the centre of this northern story, and it changes how scientists think about one of the most dangerous meeting points on the continent. To see why it is so surprising, it helps to start with the place itself, the spot where three great plates come together off the Northern California coast, and why it has long been one of the hardest puzzles in the field. Off the coast of Humboldt County, near the small city of Eureka, three of the great plates of the Earth's crust meet at a single region. Geologists call such a meeting a triple junction, and this one carries the name Mendocino. It is the busy corner where the West Coast changes its character from one kind of boundary to another. The three players are the Pacific Plate, the North American Plate, and a smaller piece called the Gorda Plate. South of the junction, the familiar arrangement holds. The Pacific Plate slides past the continent along the San Andreas system. North of the junction, everything changes. There the small Gorda Plate, along with its larger neighbour, dives down beneath the continent in the great subduction zone that runs up the Pacific Northwest. At the junction, these two very different worlds collide, and the result is a knot of faults unlike anywhere else on the coast. That knot makes the Mendocino region the most seismically restless part of California. It produces more earthquakes than anywhere else in the state, a steady drumbeat of small and moderate quakes, with a strong one every so often. Most of them rattle a sparsely populated stretch of coast and do little harm. But the same forces that make the small quakes so frequent can also make a large one, and the towns of the far north coast sit right on top of the action. For all that activity, the region has long resisted easy explanation. The simple drawing, three plates meeting at a point, is too clean for what the earthquakes actually do. Quakes there strike at odd depths and odd angles. They cluster in places the simple model does not predict. Scientists could see that the textbook sketch was incomplete, but they lacked a way to see the true shape of the rock below. The clearest sign of the mismatch was that old, strong earthquake mentioned earlier, the magnitude 7.2 that broke at a surprisingly shallow depth. In the simple picture, a quake of that kind and place should have happened deeper. Its shallowness hinted that a slab of rock was sitting where no one had drawn one, changing how and where the strain released. It was a piece that did not fit the puzzle, and for years no one could say what the missing piece was. The reason the junction is so hard to read comes back to the iceberg problem. The faults you can map at the surface are only the visible edges of structures that plunge for miles into the crust. The shape down there controls how earthquakes start, how deep they break, and how far they spread. Without that shape, any hazard estimate for the region rests on guesswork about its most important features. This is what made the new approach so valuable. The faint deep tremors are generated precisely in the hidden parts of the junction, along the surfaces where the plates and their broken fragments slide. By mapping where those tremors come from, the researchers could finally sketch the buried architecture rather than guess at it. They could test whether the simple three-plate story was enough, or whether the region hides more than three moving pieces. The answer, it turned out, was that the junction is keeping secrets. The tremors revealed pieces of rock in motion that no map had shown, fragments tucked beneath the surface and driving activity from below. The clean picture of three plates meeting at a point gave way to something more crowded and more interesting. Understanding how a swarm of tremors too faint to feel could reveal solid rock miles underground takes a moment, because the method is as remarkable as the result. It even leans on the pull of the sun and the moon. That is the next thread to follow. To trust a map drawn from tremors no one can feel, you have to trust the tremors themselves, and that means understanding what a low-frequency earthquake really is. Down where these signals are born, miles below the surface, the rock is hot enough to behave in a strange middle way. It is not fully solid and brittle like the rock near the top, and not fully molten. It is stiff but slowly yielding, and where plates grind together at those depths they do not snap cleanly. They shudder, producing small, deep, low-pitched tremors instead of sharp jolts. Each of these events is tiny, far below anything a person could sense, and far below most ordinary earthquake detection. What makes them precious is where they occur. They are made on the very surfaces where deep rock is moving, the hidden seams between plates and fragments. A normal large earthquake tells you about one violent moment in one place. A long, patient record of these faint tremors traces the living boundaries themselves, lighting up the slow grind that goes on between the big quakes. The team gathered them using a dense network of sensitive seismometers spread across the Pacific Northwest. Picking such weak signals out of the constant background noise of the planet is painstaking work. But with enough instruments and careful methods, the researchers could detect the tremors, locate where each came from, and watch where the swarms concentrated over time. Those concentrations traced the shapes of the boundaries below. Then came a clever test, the kind that turns a plausible idea into a convincing one. The researchers wanted to confirm that these tremors really mark places where rock is sliding in a particular direction. So they looked at the tides. The gravity of the sun and the moon does not only raise and lower the oceans, it also tugs very faintly on the solid Earth, flexing the crust a little as our planet turns and the moon circles. That tug is small, but it is real, and it is rhythmic. The prediction was straightforward. If the tremors come from a rock straining to move in a certain direction, then when the tidal pull happens to line up with that direction, it should give the rock a tiny extra nudge, and the tremors should grow more frequent. When the tidal pull works against the motion, the tremors should ease. The team checked, and the pattern held. The faint earthquakes rose and fell in step with the tides, exactly as they should if they mark rock sliding the way the model proposed. That result did two things at once. It confirmed that the tremors are genuine signs of deep sliding rather than random noise, and it confirmed the direction that the hidden rock is trying to move. A test that uses the moon's pull to verify the motion of buried rock is the sort of thing that sounds far-fetched until you see how cleanly it works. It anchored the whole study in something checkable. With the method trusted, the picture it produced could be trusted too, and the picture was richer than the old one. By following where the tremors clustered and which way the rock beneath them was straining, the researchers could outline boundaries that no surface map had ever shown. The faint shudders, gathered and read with care, became the outline of solid structures miles down. It is worth pausing on how indirect and how solid this is at the same time. No one saw the hidden rock. No one drilled to it. Yet by listening to its faintest tremors, checking those tremors against the pull of the tides, and mapping where they gathered, the scientists could describe shapes they will never touch. That is a good portrait of how this field works at its frontier. The Earth gives up its secrets in whispers, and the skill lies in learning to hear them. What those whispers revealed was a junction with more moving parts than the textbooks allow, including hidden fragments of rock that change the whole story of the region. Laying out that new arrangement, and the two buried pieces at its heart, is the next step. The old picture of the Mendocino Junction had three moving pieces, the three plates meeting at a corner. The new picture, drawn from the faint tremors, has 5. 2 of those pieces had never been mapped before, because they are hidden entirely below the surface. The discovery of those 2 buried fragments is the heart of the northern study, and it changes how the region's earthquakes make sense. The first hidden piece sits south of the junction and carries a name from deep geologic history. The researchers call it the Pioneer Fragment. It is a slab of old rock, a leftover from an ancient plate that mostly vanished beneath North America long ago. Most of that ancient plate is gone, swallowed by the slow machinery of the Earth. This fragment survived, and it is still in play. The Pacific Plate sliding northward is dragging the Pioneer Fragment along underneath the edge of the continent. It rides hidden beneath the surface, a piece of a vanished world still being shoved through the crust. The second hidden piece is, in a way, more startling, because it shows the continent itself coming apart at the seam. At the southern end of the Great Subduction Zone, where the ocean floor dives under the land, the researchers found that a chunk has broken off the bottom of the North American plate. That broken piece of the continent is being pulled downward along with the descending Gorda plate, dragged into the depths as the ocean slab sinks. Part of the continent, in other words, is being peeled away from below and carried down. These two fragments are what the researchers describe as the hidden drivers of the region. They are not idle, they are in motion, and their motion is part of what generates the swarms of deep tremors and helps shape where the felt earthquakes strike. The reason the junction never fit the simple three-plate sketch is that the sketch left these two pieces out. With them included, the odd depths and angles of the region's quakes start to make sense. The old shallow quake that puzzled everyone for years fits more naturally once you know a hidden slab is sitting, where the simple model showed open space. It helps to picture the whole arrangement as a slow, crowded collision, rather than a clean meeting of three plates. The Pacific Plate slides up from the south, dragging a buried relic with it. The continent presses from the east, and a piece of its underside is being torn off and pulled down. The Gorda Plate dives beneath it all from the west. 5 pieces, 2 of them out of sight, all grinding against one another in a space that the textbooks had drawn as a simple corner. The reality is a knot, and the tremors let scientists finally trace its strands. This is a discovery about structure, not about timing, and that distinction is worth holding firmly. The study did not find that a great quake is coming sooner. It found that the machine producing the quakes has more parts than anyone knew. Knowing the true number and arrangement of moving pieces is the foundation for everything else. You cannot estimate how a region will shake until you know what is down there to do the shaking. There is something fitting in how the discovery was made. The largest secrets of this junction, 2 whole fragments of moving rock, were revealed by its smallest signals, tremors too faint for any person to feel. The big quakes draw the headlines, but it was the quiet, constant murmur of the deep crust that finally drew the hidden map. The region had been speaking all along, in a voice too low to hear, until the instruments and methods caught up. What remains is to say why this matters for the people who live along that northern coast, and for how scientists rate the danger there. A more complex junction is not automatically a more dangerous one, but it does change the questions worth asking. Drawing out that meaning carefully and without overstating it is the next step before the report turns to the largest fault of them all. The natural worry, on hearing that a dangerous junction is more complicated than anyone knew, is that more complicated must mean more dangerous. That is not quite what the discovery says, and getting the meaning right matters as much as the discovery itself. The new map does not raise the odds of a great quake on the northern coast. It sharpens our understanding of a hazard that was always there. Start with what genuinely changes. For years, any estimate of earthquake danger in the Mendocino region rested on an incomplete picture of the rock below. Hazard maps, building codes, and emergency plans all draw, in the end, on a model of which faults exist, how deep they go, and how they might break. If 2 moving fragments were missing from that model, then the estimates were built on a sketch with holes in it. Filling those holes does not make the ground more dangerous. It makes the assessment of the danger more honest. That honesty cuts in more than one direction, which is why it should steady rather than frighten. A better map might reveal that certain kinds of quakes are more likely than thought, but it might equally show that others are less likely, or that the shaking from a given event would spread differently than older models assumed. The point of a sharper picture is accuracy, not alarm. The researchers were not announcing a new threat. They were repairing the foundation that any threat estimate stands on. The old puzzle of the shallow quake shows why this is more than bookkeeping. When that strong earthquake struck years ago at a depth no one expected, it was a warning that the region could surprise people. Surprises are what hurt during disasters, because preparation is built around expectations. A quake that breaks where models say it cannot is a quake that buildings and plans were not designed for. By revealing the hidden fragment that likely explains that shallow break, the new work turns a past surprise into something understood and reduces the chance of being caught off guard by the same kind of event again. There is a fresh angle worth adding here, because it links the northern story to the southern one. Both findings, the loaded gate near Los Angeles and the hidden fragments off Humboldt County, carry the same underlying lesson. Faults and plate pieces do not act in neat isolation. The southern study showed 2 faults that may break together through a gate. The northern study showed 5 pieces of rock grinding in a tangle, where the books drew 3. In both cases, the older picture was too simple, treating parts separately that actually work as a connected system. The science of the West Coast is moving steadily towards seeing these faults as members of one interacting whole. For the people who live on the far north coast, the practical takeaway is calm and familiar. The region was known to be highly active before this study, and it remains so now. The towns there already sit in one of the most earthquake-prone parts of the country, and the steps that made sense before still make sense. Secure heavy furniture, keep supplies for several days. Know that strong shaking is a normal feature of life on that coast, not a sign that something new has gone wrong. The discovery refines the science. It does not hand residents a reason for fear they did not already have grounds to respect. It also points to where the science is heading. With a better map of the junction in hand, researchers can ask sharper questions. How do the hidden fragments share strain with the visible faults? Could motion on one of them influence the great subduction zone to the north? Those are exactly the kinds of questions that the older, simpler picture could not even pose. A more complete map does not close the subject. It opens better lines of inquiry. And it points the report north, toward the largest and most consequential fault in the whole region. The junction off Humboldt County is where the sliding boundary of California gives way to something far bigger, a zone where the ocean floor dives beneath the continent along hundreds of miles of coast. That zone, called Cascadia, is the giant that scientists watch most closely of all, and it is where this story goes next. North of the Mendocino Junction, the boundary changes its nature entirely, and the fault that takes over is the largest threat on the continent. It is called the Cascadia Subduction Zone, and it runs offshore for about 700 miles from the far north of California, up past Oregon and Washington, and into the waters off British Columbia. Where the San Andreas slides side to side, Cascadia does something heavier. The floor of the Pacific Ocean dives down beneath the edge of North America. That diving motion is what makes a subduction zone the most powerful kind of fault on Earth. The ocean plate does not slip under the continent smoothly. The two get stuck across a vast surface, miles deep and hundreds of miles long, and the strain builds across that whole enormous patch. When it finally releases, the area that breaks can be immense, and the quake it makes can be far larger than anything a sliding fault like the San Andreas can produce. The biggest earthquakes ever recorded anywhere have all been on subduction zones. For a long time, people did not realize Cascadia could do this. The zone had been quiet through all of written American history. No great quake had struck it since settlers arrived, and some assumed it might be harmless, slipping along quietly rather than locking. That comfort turned out to be false, and the way scientists uncovered the truth is one of the great detective stories in earth science. The key was a single event that left its mark on 2 sides of an ocean. Researchers studying the Pacific Northwest coast found drowned forests and buried marshes, places where the land had suddenly dropped and the sea had rushed in, all at the same moment. The pattern was the signature of a massive subduction earthquake. They could date it closely from the dead trees, but they wanted the exact moment. They found it across the Pacific in Japan. Japanese records describe a tsunami that struck their coast on a winter night, a wave that arrived with no earthquake felt beforehand. A wave with no local quake meant the quake had happened far away, across the ocean. Working backward from the Japanese date and the travel time of the wave, scientists pinned the source. A great earthquake had ruptured the Cascadia zone and sent a tsunami all the way to Japan. The date was the year 1700 in late January. An ocean apart, 2 kinds of records told the same story. That discovery rewrote the hazard for the entire Pacific Northwest. Cascadia was not safe, it was loaded, and it had produced a giant quake just a few centuries before, well within the span that such faults repeat. The drowned forests in the Japanese wave proved that the cities of the Northwest sit in the shadow of a fault capable of one of the largest earthquakes the planet can make, followed by a tsunami racing toward their own shores. The sediment record showed this had happened many times. By reading layers on the ocean floor, researchers found that Cascadia has produced great earthquakes again and again over thousands of years, spaced a few centuries apart on average. The quake of 1700 was just the most recent in a long line. Enough time has now passed since then that the zone is considered capable of another great rupture, though, as always, no one can say when. This is the fault that earns the name the big one in the Pacific Northwest, distinct from the San Andreas worry to the south. A great Cascadia quake would shake Portland, Seattle, and the coastal towns between them, and the tsunami it spawned would reach the shore in minutes, too fast to outrun from low ground. It is the scenario that drives much of the region's preparation, and the reason scientists watch the zone so closely. For most of the time since the 1700 quake, scientists studied Cascadia and the San Andreas as separate problems. They are different kinds of faults, hundreds of miles apart, governed by different motions. It seemed natural to treat the southern sliding faults and the northern diving zone as two unrelated dangers, each on its own clock. That assumption felt safe and sensible. The work of this past year began to question it. A study published in the spring suggested that these two giants, the sliding San Andreas and the diving Cascadia, may not be as independent as everyone assumed. They might at times move in step. That possibility, and the careful evidence behind it, is the next thread, and it ties the whole coast into a single uneasy system. The spring study came out of work led by a marine geologist who has spent decades reading the earthquake history written in the seafloor. Its central idea is one that scientists had floated before, but rarely managed to support with hard evidence. The northern San Andreas and the Cascadia subduction zone, the study proposed, may sometimes rupture in close succession, partly synchronized rather than acting on wholly separate clocks. The lead researcher framed the stakes in plain words. People are used to thinking of Cascadia, the Great Northwest Quake, as the catastrophic worst case for the region. His findings suggested that the true worst case might be larger still. It might not be Cascadia alone. It might be Cascadia and the northern San Andreas going off together, or one right after the other, within a span far too short for the country to recover between them. The two faults meet, in a sense, at the Mendocino Junction explored earlier in this report. The northern end of the San Andreas runs up to that knotted corner, and the southern end of Cascadia begins nearby. They are neighbours at the junction, even though they are very different kinds of faults. That shared corner is part of why a break on one might disturb the other. A great rupture on either could deliver a powerful jolt to the region where they nearly meet, and that jolt could help tip an already loaded neighbour into slipping. The evidence for this connection did not come from watching it happen. No one has seen these faults break together in the era of instruments. Instead, it came from the long memory of the sea floor, from layers of sediment that record ancient earthquakes going back thousands of years. By matching the timing of past quakes on the two faults, the researchers found cases where the records line up closely enough to suggest the faults broke at nearly the same time. The strength of the claim rests on how often that lining up occurs, and the team was careful about it. They did not claim the faults always move together. They found partial synchronization, a tendency to sometimes break in close succession, not an iron rule. Across the long record they reconstructed, they pointed to several instances over the last 1500 years where the two appear to have ruptured within a very short window of each other, including the most recent great events. It is worth being honest that pinning down the exact timing between two ancient quakes is genuinely hard, and the researchers said so. Sediment layers give approximate dates, not precise ones. Two quakes that look simultaneous in the record might be separated by years that the sediment cannot resolve. The team acknowledged this directly. Their case is that the alignment appears more often than chance would explain, not that every pairing is certain. That is a measured claim, and it is stronger for being modest. What gives the idea real weight is that the world has actually seen something like it. The researchers pointed to a documented case from recent history, off the coast of Sumatra. There, two enormous subduction earthquakes struck close together in time, the second following the first by a matter of months. It proved that one great quake on a subduction zone really can be followed soon after by another large quake nearby. The thing the Cascadia study proposes is not a fantasy. It has a real recorded precedent on the other side of the world. The reason this matters so much comes down to recovery and resources. A single great quake on either fault would, by itself, pull in the emergency resources of the entire nation to respond. If both struck close together, the researcher noted, the country could face San Francisco, Portland, Seattle, and Vancouver all in crisis at once, in a compressed span of time, with the resources to help any one of them stretched across all of them. That is what makes the joint scenario worse than the sum of its parts. To understand how anyone can read the timing of quakes from thousands of years ago, the report has to look at the sediment record itself, the patient archive on the ocean floor that made this study possible. That archive is the next piece. The evidence for both the synchronization study and much of what we know about Cascadia comes from a quiet, muddy archive at the bottom of the sea. To read the deep past of these faults, scientists go offshore and pull up long tubes of sediment from the ocean floor called cores. Each core is a slender column of the mud and sand that has settled there over thousands of years, layer upon layer, the oldest at the bottom and the youngest on top. Most of the time, that settling is slow and gentle. Fine particles drift down and build up grain by grain, year after year, making smooth, even layers. A core through that quiet sediment is mostly uniform, a record of long stretches when nothing dramatic happened. But every so often, the cores show something different, a sudden coarse layer that interrupts the calm, and those layers are the prize. These coarse layers are called turbidites, and they are the fingerprints of underwater landslides. When the seafloor shakes hard enough, the loose sediment piled on the continental slope lets go and rushes downhill in a dense, muddy avalanche. That avalanche carries coarse material out across the deep floor and drops it in a distinct layer, settling out from heavy to fine. A strong earthquake is one of the few things that can shake a whole region's seafloor at once and trigger these slides along a long stretch of coast. So a turbidite layer in a core is, in many cases, the trace of an ancient earthquake. Find the same layer in cores taken from many places along the coast, all at the same depth and the same age, and you have strong evidence that a single great quake shook the entire region at one moment, setting off slides everywhere along its length. The depth of the layer tells you its order in time. The material in it can be dated. Layer by layer, the cores become a calendar of past great earthquakes. The marine geologist who led the synchronization study has spent much of his career building exactly this kind of calendar for Cascadia and the northern San Andreas. The cores his team worked with preserve more than 3,000 years of history, a stack of quiet sediment punctuated by the coarse marks of great quakes. By counting and dating those marks, researchers can estimate how often each fault has ruptured and roughly when. The synchronization idea grew out of comparing those two calendars side by side. If the turbidite from a San Andreas quake and the turbidite from a Cascadia quake repeatedly sit at the same age in their respective cores, that points to the two faults breaking at nearly the same time. It was this matching of dated layers, fault against fault across thousands of years, that revealed the cases where the giants appear to have moved together. The method is not flawless, and the field knows it. Dating sediment carries uncertainty, and not every coarse layer comes from an earthquake, since storms and other forces can also stir the sea floor. There has even been honest debate within the field about how cleanly the Cascadia record can be read, with some researchers questioning how reliably every layer can be tied to a specific quake. That debate is a healthy sign. It means the records are being tested hard rather than taken on faith, and the conclusions that survive that testing are the sturdier for it. What stands out, stepping back, is how much of our knowledge about the largest earthquakes rests on this slow reading of mud. The great quakes themselves are rare, far too rare to study by waiting for them, but each one leaves a mark in the sediment, and those marks accumulate into a long record that no human memory could hold. By pulling up cores and reading their layers, scientists effectively interview earthquakes that struck before any written history of the coast existed. That long record is what lets researchers speak about a worst case that no living person has seen, the two great faults breaking close together. Laying out that scenario plainly, and what the Sumatra precedent really tells us about it, is the next step. The scenario at the centre of the spring study is simple to state and sobering to sit with. Two of the largest faults on the west coast, the Cascadia subduction zone and the northern San Andreas, might rupture close together in time, not necessarily in the same instant, but within a window short enough that the second strikes while the first is still an open wound. The study's author called the usual single Cascadia quake the thing people brace for, and then suggested the real worst case is the pair. To feel the weight of that, picture the reach of each fault on its own. A great Cascadia rupture would shake the coastal northwest, from northern California through Oregon and Washington, and send a tsunami onto those shores within minutes. A great northern San Andreas rupture would devastate the San Francisco Bay region, as its predecessor did more than a century ago. Each of these, alone, ranks among the worst natural disasters the country could face. The scenario asks what happens if they arrive nearly together. The answer is not simply twice the damage, it is worse than double, because of how disaster response works. When one region is struck, help flows in from everywhere else. Rescue teams, supplies, power crews, and money pour toward the disaster from across the nation and beyond. That flow is what lets a stricken area begin to recover. The whole system assumes that while one place is down, the rest stand ready to lift it. A joint rupture breaks that assumption. If San Francisco, Portland, Seattle, and the coastal towns between them all fall into crisis at once, there is no unscathed neighbour close by to send the bulk of the help. The resources that would pour into a single disaster must instead be split among several, each enormous, all at the same time. The researcher put it directly. A single quake on either fault would draw down the resources of the whole country. Both together would leave the entire west coast in emergency at once, in a compressed span, with help spread thin across all of it. The reasonable response to a scenario like this is to ask how seriously to take it, and that is where the Sumatra case earns its place. Off the coast of Sumatra, the world watched two giant subduction earthquakes strike close together. The first, in late 2004, was the Great Quake that caused the catastrophic Indian Ocean tsunami. The second, a separate enormous quake on the adjacent stretch of the same fault system, struck about 3 months later. One great quake had been followed, within a season, by another nearby. That sequence is the reason the West Coast scenario cannot be dismissed as far-fetched. Until Sumatra, the idea that one giant subduction quake could be closely followed by another was largely theoretical. Sumatra made it real and observed. It showed that a great rupture can change the strain on a neighbouring section, enough to bring it to the point of breaking, and that the wait between them can be months rather than centuries. The West Coast pairing the study proposes is the same kind of event, neighbours nudging neighbours toward release. It is important, though, to keep this scenario in its proper place, because the study itself does. The finding is about a tendency seen in the long record and a possibility supported by precedent. It is not a forecast that the next Cascadia quake will drag the San Andreas with it, or the reverse. The faults have also broken alone many times. The synchronization is partial, an inclination that shows up across the record, not a rule that binds the two together every time. So the honest summary is this: the worst credible case for the West Coast may be larger than a single great quake, because the largest faults appear to interact and have a recorded habit, elsewhere in the world, of breaking in close pairs. That widens the worst case without making it more imminent. It is a reason to plan more broadly, not a reason to expect disaster tomorrow. While these long-term findings filled the journals, the faults themselves were not silent. Through the spring, a series of small offshore quakes and swarms rattled the coast and made headlines, and they offer a useful, smaller-scale view of how this system behaves day to day. Those recent events are the next thread. While the big studies described deep time, the ocean off the coast kept producing earthquakes that people could read about the same week they happened. Through the spring of this year, a series of offshore quakes and swarms drew attention up and down the west coast, and they put the long-term findings in a more immediate frame. In early June, a magnitude 5.7 earthquake struck about 100 miles off the southern coast of Oregon, out beyond the small community of Pistol River. It was a solid, moderate quake, the kind that would be strongly felt if it struck on land near a town, but it broke far offshore in open water. It came at a shallow depth of roughly 6 miles. The agencies that watch for tsunamis checked it and issued no warning. It generated no dangerous wave and it caused no damage on shore. 2 other earthquakes rattled elsewhere along the coast the same day, none of them harmful. Weeks earlier, in the spring, an even busier sequence struck far off the coast of Washington. Overnight, a swarm of at least 18 earthquakes broke out, the largest around magnitude 4.2. They clustered at a spot roughly 250 miles offshore, well out into the Pacific. The regional seismic network tracked the swarm through the early morning hours and was quick to reassure the public. The quakes were far out to sea, not strong enough to make a tsunami, and posed no hazard to communities on land. These offshore events shared an important feature that kept them from being a true Cascadia worry. Most of them did not happen on the Cascadia subduction zone itself. They struck along a separate fault system called the Blanco Fracture Zone, a band of faults far offshore where pieces of the ocean floor slide past each other. The Blanco Zone is one of the most active stretches of fault in the region, and it produces frequent moderate quakes. But it sits well out to sea, away from the locked subduction zone that threatens the coast, and its quakes do not carry the same danger. The seismic networks were careful to make that distinction each time, and the care is worth noticing. When the Washington swarm hit, scientists noted plainly that the quakes were far from the Cascadia subduction zone, and also that they were not coming from a particular undersea volcano that researchers keep an eye on. Both clarifications were aimed at heading off needless alarm. The events were real and worth recording, but they were happening in a place and on a fault that did not threaten people. Still, these clusters drew heightened interest precisely because of where the West Coast sits. Any notable seismic activity in the Pacific Northwest tends to raise the same question in people's minds, the question of whether this is the start of something bigger. That instinct is understandable, given Cascadia's long-term potential. The event served, more than anything, as reminders that the entire coastline rests on a powerful and constantly moving system, even when the day's particular quakes pose no threat. It is worth being clear about what these spring events did and did not signify, because the temptation is to read too much into them. They were not foreshocks of the Great Quake. They were not signs that the loaded faults to the south were about to break. They were ordinary, if attention-catching, activity on an active offshore fault system, the normal background grumble of a restless boundary. The coast produces such events regularly, and most years pass with many of them and no disaster. What they do offer is a window into the living system. Each small quake is the same machine at work that produces the great ones, just at a scale that does no harm. The plates grind, the offshore faults slip, the seafloor shudders, and the instruments record it all. Watching the small events is part of how scientists keep their finger on the pulse of the boundary, even though no single small quake tells them when a large one will come. That last point deserves its own careful treatment, because the relationship between small quakes, swarms, and the large quake everyone worries about is widely misunderstood. Sorting out what a swarm of small earthquakes actually means, and what it does not, is the next step. A swarm of small earthquakes makes people uneasy in a particular way. It feels like a build-up, like the ground clearing its throat before something larger. That instinct is worth taking seriously and then examining honestly, because the truth about swarms is more reassuring and more interesting than the fear suggests. First, it helps to know what scientists even mean by a swarm. Most earthquake sequences follow a familiar shape. A main quake strikes, the largest of the bunch, and then a string of smaller aftershocks follows as the ground settles. A swarm breaks that pattern. It is a cluster of small to moderate quakes in one area over some stretch of time, with no single dominant main shock. The largest quake in a swarm might come in the middle of the sequence, or near the end rather than first. The events just keep coming, roughly similar in size without the clean main shock and aftershock structure. The agencies that study this are frank that the line between a swarm and an ordinary sequence is not sharp. There is no precise threshold where a string of quakes officially becomes a swarm. Real sequences fall along a spectrum from very much like the main shock and aftershock pattern to very much unlike it. The swarm label is simply applied when many quakes happen close together in a small area without fitting the usual shape. It is a description, not a diagnosis of something gone wrong. Now to the heart of the worry. Does a swarm mean a big quake is coming? The honest answer is almost always no. The overwhelming majority of swarms simply run their course and fade, having released a little energy and changed nothing about the larger picture. Swarms are common, especially in active areas like the offshore faults of the Pacific Northwest and the restless ground of the Mendocino region. Great quakes are rare. Most swarms are not followed by anything large at all. There is a grain of truth inside the fear, and it should be stated plainly rather than hidden. Any small earthquake very slightly raises the odds that a larger one will follow, simply because quakes can trigger other quakes nearby. In a heavily loaded fault system, a swarm could, in principle, be the nudge that helps set off something bigger. But that raised probability is tiny. It shifts the odds from very small to slightly less small. It does not turn a swarm into a reliable warning. The vast majority of the time, the slightly raised risk passes without event. This is why scientists almost never issue alarms based on swarms alone, and why the calm tone of the agencies during the spring events was not carelessness. It was accuracy. When a swarm struck off Washington, the responsible thing was to note it, locate it, confirm it posed no immediate hazard, and keep watching. Raising an alarm every time a swarm appeared would mean crying wolf constantly, since the wolf almost never comes. The measured response is the correct one. The deeper reason swarms cannot serve as warnings comes back to a hard fact that runs through this whole report. No one can predict the exact time and place of an earthquake. The agencies state this flatly and repeat it often. Despite a century of effort, no reliable method exists to forecast a specific quake from any precursor, swarms included. Faults do not give a clear, consistent signal before they break. Sometimes great quakes come with no warning at all. Sometimes swarms rumble for weeks and produce nothing. The link between the small and the large is too loose to predict from. What swarms do offer is information of a different kind. They show scientists where faults are active, how the ground is behaving in a region, and how strain is being released in small increments. They are data, valuable for understanding the system, even though they are not warnings of a date. That distinction between learning about a fault and predicting its next move sits at the very centre of where this science can and cannot go. And that brings the report to the hardest and most honest part of the whole story, the part the title points to directly. The phrase that scientists do not know why these faults are stirring deserves a careful, fair answer, because it is partly true and partly a misunderstanding. Sorting out exactly what is known and what is not is the next step. The title that opened this report carries a claim worth meeting head-on. It says scientists do not know why the West Coast faults are coming back to life. That phrase is partly fair and partly misleading, and the honest version of the answer is more interesting than either a flat yes or a flat no. Start with what scientists do know, because it is a great deal. They know why these faults exist and what drives them. The grinding of the Pacific and North American plates, a couple of inches a year, is well measured and well understood. They know that locked faults store strain and release it in quakes. They know, in broad terms, where the major faults run, which sections lock and which creep, and roughly how often the great ones have broken in the past. The basic engine of West Coast earthquakes is not a mystery. It is one of the better understood systems in all of Earth science. So in the largest sense, scientists do know why the faults move. They are not baffled by the existence of earthquakes on the San Andreas or Cascadia. The boundary has behaved this way for millions of years, and the physics of it is clear. If the title meant that the basic cause is unknown, that would simply be wrong, and it would be unfair to the people who have spent careers mapping this system. But there is a real and honest sense in which the phrase holds, and it is worth granting fully. The specific, detailed questions, the ones that would let scientists actually predict and fully explain the behaviour of these faults, remain genuinely open. Why is the strain on the southern San Andreas at a 1,000-year high right now, rather than 50 years ago or 50 years from now? Why do the great faults appear to sometimes synchronize and sometimes not? What exactly are the hidden fragments at the Mendocino Junction doing, and how do they share strain with the faults around them? These are real unknowns, and the year's studies opened more of them than they closed. The deepest unknown of all is the one that matters most to people, and the field is honest about it. No one can predict when a specific earthquake will strike. After more than a century of intense study, with dense networks of instruments and powerful computers, the timing of the next great quake on any of these faults remains beyond reach. Scientists can estimate odds over decades. They cannot name a year, let alone a day. That limit is not for lack of effort. It appears to be a deep feature of how faults work, a genuine frontier rather than a temporary gap. There is a subtler point hidden in the title's phrase, and the year's findings illustrate it well. Each of the new studies revealed that the faults are more complex than the simpler models assumed. The southern faults interact through a gate. The northern junction has hidden moving pieces. The great faults may synchronize. In every case, scientists discovered that their picture was incomplete, that the system had parts and connections they had not fully accounted for. In that sense, the faults really are surprising the experts, not because the experts are lost, but because the system keeps proving richer than the current map. So here is the fair reading of the title. The faults are not coming back to life in the sense of waking from sleep. They never stopped, and scientists are not clueless about why they move. But the faults are revealing new complexity. The strain on some has reached unusual highs, and the precise behaviour of the system, above all its timing, remains genuinely unknown. The mystery is real, but it is a mystery of detail and prediction, not of basic cause. Holding both halves of that truth at once is the mature way to read all the year's news. The science is strong and getting stronger, the system is better mapped than ever, and at the same time, the most important practical question, when, stays unanswered, and each new study uncovers fresh puzzles. To make that balance concrete and useful, it helps to draw a clear line between the settled facts and the open questions, plainly, side by side. That accounting is the next step. It helps, after so many findings, to set them down in two plain columns. On one side, what scientists are confident about. On the other, what remains a real question. Drawing that line clearly is the antidote to both panic and false comfort, because it shows exactly how much is solid ground and how much is still open water. Begin with the settled side. It is confirmed that the southern San Andreas and the neighbouring San Jacinto fault are locked and carrying very high strain, with the recent estimate placing it at a 1,000-year peak across the junction between them. It is confirmed that the Cajon Pass can act as a gate that may let a rupture spread from one of those faults to the other. It is confirmed that a joint rupture across that gate could reach a magnitude in the range of 7.4 to 7.8, large enough to shake a wide inland swath of Southern California at once. The confirmed list continues to the north. It is established that the Mendocino Junction off Northern California is more complex than the old three-plate picture, with the recent study mapping 5 moving pieces including 2 hidden fragments below the surface. It is established that Cascadia is a subduction zone capable of one of the largest earthquakes on Earth, and that it last produced a great quake in the year 1700, dated firmly by drowned forests and a recorded tsunami in Japan. It is established that these faults have broken many times across the long sediment record, on the order of every few centuries for the great ones. Now the uncertain side stated just as plainly. The exact timing of any future quake on any of these faults is unknown and, by every current method, unknowable. The 1,000-year strain figure is a careful estimate built from models and dated past quakes, not a direct reading, and it carries real margins of error. Whether the San Andreas and Cascadia truly synchronize is a proposal supported by matching sediment layers and one foreign precedent, not a settled fact, and the difficulty of dating ancient quakes leaves the timing of past pairings fuzzy. More open questions sit alongside those. Exactly how the hidden fragments at the Mendocino Junction share strain with the visible faults is not yet worked out. Whether a swarm or a moderate offshore quake could nudge a loaded fault toward release is understood only in the loosest probabilistic terms. And the central why of the title, why the strain and the activity have reached their current state at this particular moment, is not answerable in the detailed way that would allow prediction. Seeing the two columns together corrects the natural distortions. If you read only the confirmed side, you might feel the situation is fully understood, and therefore either safe or doomed, both of which overstate the certainty. If you read only the uncertain side, you might feel scientists know nothing, which badly undersells a strong and growing body of knowledge. The truth lives in holding both columns at once. A great deal is known about what these faults are and what they can do. The timing and many of the fine mechanisms remain genuinely open. This balance also explains why the responsible message from every researcher this year was the same, and why it was calm. None of them said disaster is imminent, none said there is nothing to worry about. They said, in their own words, that the risk is significant and the conditions warrant preparation now rather than later. That is the only message the two columns support. The confirmed dangers justify preparing. The honest uncertainties forbid panic, since no one can say the threat is near. There is one more reason this accounting matters. It shows that the gaps in knowledge are not signs of failure but the working edge of an active science. Each open question on the uncertain side is something researchers are now equipped to study, often with the very tools that produce this year's findings. The line between known and unknown is not fixed. It moves slowly as the faint tremors are mapped and the sediment is read and the models are refined. Among those open questions, a few sit right at the frontier, where scientists are probing the subtlest forces that act on faults, including, remarkably, the pull of the sun and the moon. Those frontier forces, and what they hint about the future of this science, are the next step. At the leading edge of this research sit forces so faint they were long dismissed, yet they are turning out to carry real information about how faults behave. The clearest example already appeared in this report, in the test that used the tides to confirm the hidden tremors off Northern California. That same idea, that tiny, gentle forces can reveal and even influence the behavior of faults, is one of the liveliest frontiers in the field. Recall how the tidal test worked, because it captures the whole frontier in one elegant move. The gravity of the sun and the moon pulls on the solid Earth, flexing the crust slightly as the planet turns and the moon circles. When that pull happened to line up with the direction the hidden rock wanted to move, the faint, deep tremors grew more frequent. When it opposed that motion, they eased. The rock was sensitive enough to feel the difference between a tide that helped and a tide that hindered, and it answered with more or fewer tremors. That sensitivity is remarkable when you sit with it. The tidal force on the crust is extraordinarily small, far too weak to trigger a real earthquake on its own. Yet the deep tremors responded to it clearly enough to confirm both that they are genuine and which way the rock is straining. This tells scientists something important. A fault near its breaking point is exquisitely balanced, so finely poised that even a whisper of extra force can change how it behaves at the margins. The tides do not cause great quakes, but they can modulate the faint background activity, and that modulation is a readable signal. This opens a way of thinking that runs through much of the current research. If a fault responds to the tiny pull of the tides, it likely responds to other small forces too. The passing of a distant large earthquake sends seismic waves rippling through the planet, and those waves can briefly stress faults far away, sometimes setting off small quakes thousands of miles from the source. Slow, quiet slip events, where a fault creeps a little over days or weeks without a felt quake, can shift strain onto neighbouring locked patches. The picture emerging is of faults as sensitive systems, nudged by an array of subtle influences rather than sitting inert until they break. The synchronization idea between the San Andreas and Cascadia belongs to this same frontier. The proposal that one great fault could help trigger another, even across the distance between them, is a story about faults influencing faults through the strain they pass to one another. The Sumatra pair, where one giant quake was followed within months by another nearby, is the same physics at full scale. Small or large, the theme is connection. Faults feel each other, and feel the forces around them, more than the older, isolated models allowed. What makes this frontier so promising is that the tools to study it have finally arrived. Dense networks of sensitive instruments can now catch the faint tremors and the slow slips that older sensors missed entirely. Powerful computing can sift mountains of data for the subtle patterns, like the tidal response, that reveal how faults are behaving deep down. Much of what was discovered this year was possible only because the instruments and methods crossed a threshold that let scientists hear the quiet conversation of the crust. It is worth being clear about what this frontier does and does not promise, to keep expectations honest. Understanding that faults are sensitive and connected does not, by itself, bring earthquake prediction within reach. Knowing that tides modulate tremors, or that faults can trigger one another, adds to the understanding of the system without yielding a way to name the date of the next great quake. The frontier is advancing the science of how faults work, not delivering a forecast. That distinction has held through every advance so far, and there is no sign yet that it is about to fall. Still, the direction is genuinely hopeful. Each subtle force that scientists learn to read is another window into the hidden life of faults, another way the silent crust can be made to speak. The faults are not becoming more dangerous as this research advances. They are becoming better understood, their behaviour less of a closed book. That growing understanding is most useful when it reaches the people who live on this ground, in the form of plain, practical steps that turn knowledge into safety. What those steps are, and why they remain calm rather than fearful, is the next part of the report. For everything this report has covered about strain gauges and hidden fragments and synchronized giants, the practical advice for someone living on the West Coast is refreshingly simple, and it has not changed because of this year's findings. The new studies sharpen the science. They do not call for a new way of life. The steps that made sense before still make sense, and they are the same steps that experts have recommended for years. The foundation is preparation at home, and it costs little. Keep enough water and food to last your household several days without resupply, because a major quake can cut water lines and close roads for exactly that long. A gallon of water per person per day, stored where you can reach it, is the standard guide. Add a flashlight, a basic first aid kit, any medicines you depend on, and a way to hear official information when the power is out. None of this is exotic. It is the same kit that serves for any disaster, and assembling it is an afternoon's work, not a project. Inside the home, a little securing goes a long way, because much of the harm in a quake comes from objects, not collapse. Heavy furniture like bookcases and dressers can be strapped or bolted to wall studs so they cannot topple onto someone. A water heater can be braced so it does not tip and break its lines. Heavy items are better stored low than high. These fixes are cheap and quiet, and they address the most common injuries, which come from things falling during the shaking rather than from buildings coming down. When the shaking actually starts, the official guidance is short and worth knowing by heart. Drop to the ground, take cover under something sturdy like a solid table, and hold on to it until the shaking stops. The instinct to run outside is usually the wrong one, since most injuries happen when people move during the shaking and are struck by falling objects or stumble. If there is no sturdy cover nearby, get low against an interior wall, away from windows, and protect your head and neck with your arms. Stay put until the ground is still. The coast adds one more rule, and it is the one that saves the most lives there. If you are near the shore and feel a strong or long earthquake, do not wait for an official warning. Move to high ground or inland as soon as the shaking lets you, on foot if the roads are blocked. A great quake on Cascadia would send a tsunami onto the nearest shores within minutes, far too fast for any alert to outrun. The shaking itself is the warning. For people in low coastal areas, knowing the route to high ground and taking it without hesitation is the single most important piece of preparation. It is worth saying clearly why this guidance is calm rather than urgent in tone, because the calm is deliberate and correct. None of the year's findings means a quake is coming soon. They mean the long-term risk is real, and in places, higher than the simplest models showed. The right response to a real but untimed risk is steady preparation, the kind you do once and then largely forget, not anxious waiting. People who live in earthquake country do not spend their days afraid. They prepare sensibly and then get on with life, which is exactly the right posture. There is also comfort in numbers and in time. These faults have been loaded and capable for a long time, and most days, months, and years pass without a great quake. Preparation is insurance against an event that is serious but not imminent, the same way you wear a seatbelt without expecting a crash on every drive. The household that has water stored and furniture secured has done the meaningful work. It can then treat the science as something to follow with interest rather than dread. The thread that makes all of this possible, from the household plan to the tsunami rule, is the constant work of watching the faults, the networks of instruments and the warning systems that turn raw tremors into useful alerts. How that watching works, and how it is steadily improving, is the next step before the report draws to a close. Behind every finding in this report stands an unglamorous foundation, the constant, patient work of watching the faults. Across the West Coast, a dense web of instruments listens to the ground every second of every day. These are seismometers, sensors so finely tuned they can detect the faint, deep tremors described earlier, thousands of times weaker than anything a person could feel. They are buried in vaults, set in boreholes, and spread across the landscape in networks that cover the entire boundary. The data from these instruments flows constantly into monitoring centres run by government surveys and universities. There, the signals are gathered, analysed, and turned into the catalogues of earthquakes that scientists and the public rely on. When a quake strikes anywhere on the coast, this system locates it, measures its size and reports it within minutes, often within a minute or two. The swarms and offshore quakes of the spring were tracked this way, located and sized and assessed for hazard almost as they happened. That speed is what lets agencies reassure the public quickly and accurately. This same network is the source of the deeper discoveries too, not just the daily reports. The hidden fragments off Northern California were found by mining the faint tremors that a dense seismometer network recorded. The strain estimates and the fault models all rest, in the end, on years of accumulated data from these instruments. The watching is not only an early warning service, it is the raw material of the science, the long record that lets researchers see patterns no single quake could reveal. In recent years, the watching has gained a new and powerful ability, the capacity to warn people in the seconds before shaking arrives. The West Coast now has an earthquake early warning system built on that same instrument network. The idea behind it is elegant and rooted in simple physics. When a fault breaks, it sends out different kinds of waves. The first to arrive are fast and relatively gentle. The destructive shaking follows a little behind, moving more slowly. Instruments near the fault can catch that first fast wave, recognize that a large quake has begun, and send an alert ahead electronically, faster than the damaging waves can travel. The warning that buys is short, but short can be enough. Depending on how far you are from the fault, the alert might give you a few seconds to tens of seconds before the strong shaking reaches you. That is not time to flee far, but it is time to drop and take cover, to pull a car to the roadside, to step back from a hazard. On a larger scale, those same seconds can let automatic systems slow trains, stop elevators at the nearest floor, and pause delicate industrial processes before the shaking hits. Lives and equipment are saved in the gap between the warning and the wave. It is important to be clear about what this system is and is not, to avoid a common confusion. Early warning is not prediction. It does not tell you a quake is coming tomorrow. It detects a quake that has already started and races a message ahead of its slower waves. The distinction matters. Prediction, naming the time of a future quake, remains beyond reach. Early warning, alerting people to a quake already underway, is real and working now. One looks into an unknowable future. The other simply outruns a wave that has already left the gate. The watching keeps improving, and that steady progress is one of the more hopeful threads in the whole story. Networks grow denser, methods grow sharper, as the discovery of the hidden tremors showed. The early warning system widens its reach and shortens its response. Offshore, new instruments are slowly being placed on the seafloor to watch the parts of Cascadia that land-based sensors can barely sense. Each improvement adds a little more sight to a system that, not long ago, was largely blind to the faint signals now being read. That progress is the right note on which to gather the whole report together. The faults are powerful and, in places, more loaded and more complex than older models showed. But the ability to watch them, understand them, and warn against them has never been greater. To close, it helps to return to where this began, to the event that opened the report, and to set down plainly what is known, what is uncertain, and what to watch for next. This report began with a single finding, reported this past June. A stretch of the San Andreas Fault in Southern California, together with the neighbouring San Jacinto, is carrying more strain than it has in about 1,000 years, locked and loaded where the two faults nearly meet near the Cajon Pass, less than 60 miles from Los Angeles. That finding is where the story started, and it is the right place to end, with the whole picture gathered around it. What is known can be stated with confidence. The strain on those southern faults is real and high, by careful estimate at a 1,000-year peak. The pass between them can act as a gate, and a rupture that crosses it could reach a magnitude near 7.4 to 7.8, shaking a wide inland stretch of Southern California at once. To the north, the Mendocino Junction is more complex than anyone had mapped, with hidden fragments of rock in motion below the surface. Beyond it, Cascadia stands as a giant capable of one of the largest quakes on Earth, last broken in the year 1700, and new work suggests it and the San Andreas may sometimes break in close succession. These are solid findings, built from instruments, sediment cores, and careful models. What is uncertain is just as important to hold clearly. No one can say when any of these faults will break. The timing is unknown, and by every method available, unknowable. The 1,000-year strain figure is a careful estimate with real margins. The synchronization of the great faults is a supported proposal, not a settled fact. The fine mechanisms, how the hidden fragments share strain, how one fault might trigger another, remain open questions that this year's studies opened more than they closed. The science is strong, and it is honest about its edges. The title asked whether the faults are coming back to life, and whether scientists know why. The fair answer threads between the two extremes. The faults never slept, so they are not waking. But the strain on some has climbed to unusual highs, and each new study reveals a system more complex and more connected than the old maps showed. Scientists understand the basic engine well. They cannot yet predict its timing or fully explain its finest behaviour. The mystery is genuine, but it is a mystery of detail and prediction, not of basic cause. As for what to watch next, the honest guidance points not to a date but to the work itself. Watch for the monitoring networks to grow denser and the early warning system to widen, especially offshore where Cascadia has been hardest to see. Watch for new studies that test the synchronization idea against more sediment records and that map the hidden fragments in finer detail. Watch, if you live there, by doing the simple, settled things, storing water, securing heavy furniture, and knowing the route to high ground near the coast. Those steps answer the part of the risk that is real and within your control. The steadying truth, underneath all of it, is that none of this is new in kind. The West Coast has lived on a moving boundary for millions of years, and the people who settle there have always shared the ground with these faults. What is new is not the danger, it is the clarity. We can see more of the system now than ever before, read its faintest tremors, weigh its stored strain, and trace its hidden pieces. That clarity is a gift, even when part of what it reveals is how much remains unknown. So the faults grind on, a couple of inches a year, as they have all along. The instruments listen. The researchers read the mud and model the strain and refine the map, and the rest of us prepare what we can prepare and then live our lives on this restless, beautiful coast, informed rather than afraid. The next report will follow the science as it moves, and bring you what the ground reveals when it does.